In this lecture, we are going to talk about Lefschetz fixed point theorem. So say you have a map F, it's a continuous map between simplicial complexes from x to x. So we already know that this map is going to induce map between the homology groups. So this map F will induce map between homology groups. So you have this map phi k from hk to hk of x. So obviously you have phi 0 from h0 to h0, then you have phi 1 from h1 to h1, then you have phi 2 h2 to h2, and so on. Now in these maps we can modulo out the torsion. So this is important. In Lefschetz fixed point theorem we modulo out any torsion. So then the maps just becomes phi k from some zn to zn. So you have modulo out any torsion. So for example, if you're working with projective space, you just consider these integers. So you do not consider this z modulo 2z. So you get rid of all the torsion. So now you have this map phi k from zn to zn. So obviously again there are large number of maps like this. You have phi 0, phi 1, phi 2, and so on. So this is mapping the zn to zn. That means it is a n by n matrix, and with entries in z, so we can take the trace of the matrix. So trace of the matrix is just the sum of the elements lying on the diagonal. So we can compute the trace of this matrix and denote it as trace phi k. So first thing we need to define is Lefschetz number. So this is written as lambda of f. This is just k greater or equal to 0 minus 1 to the power of k trace of phi k. So you consider h0 and see what the matrix is, add the diagonal elements. You have phi 0, then you compute phi 1, which is from h1 to h1, and then see what the matrix is, and so on. So instead of integers, we can use rational numbers or real numbers. This you can just change using universal coefficient theorem. So let us see an example. So say space X is contractible space and F is the map from X to X. So then this H0 of X is just integers and all other groups are 0. So all HIX are 0 except the 0 which is integers. So you have this map phi 0 which is from H0 to H0, which is from Z to Z. So this is just the identity map. And so obviously then trace of this is just 1 because this is just multiplication by 1. So trace is just 1. So trace of phi 0 is 1. And rest of the homology groups are 0. So this entire thing collapses to just 0. So minus 1 to the 0 times trace of phi 0. So this is just 1. So there's an important remark here which we will state after we state the theorem. So another example is, so in case you have an identity map, so f is an identity map from x to x, then phi of k is just the identity matrix from this hk to hk. So this is an identity matrix. So say this hk is of the form zn, then you have identity matrix from zn to zn, so which will have 1 on the diagonal element. So the diagonal is just considered as 1 1 1 1. You add it up, you get n, which is the dimension of this space. So the trace is just the dimension of hkx because trace is just identity matrix n by n. So you add the diagonal elements, you get n, which is the dimension if we are saying that hk is zn. So then this lambda of identity map so is just the Euler characteristic. So notice that for Euler characteristic again we have minus 1 to the power of k, and then you have dimension of hk. So instead of trace you have dimension of hk, and the trace is the dimension of hk in this case. So let us now come and define the theorem. So the Lefschetz fixed point theorem is, if x is a finite simplicial complex and you have a map f from x to x with lambda of f not 0, then f has a fixed point. So this finite simplicial complex is important. So you need this compactness condition, and that we will see here. So notice that here now lambda of f is 1, so lambda of f is not 0. But this theorem here does not apply to just a contractible space, because sometimes the space might not be compact. For example, you can have a map from real line to itself, say x maps to x plus 1. This will not have any fixed point. So this is a map from reals to reals. Obviously reals are contractible, so this example 1 applies. And then you have lambda of f equals to 1. So this is not 0, but it does not have any fixed point, precisely because again we need finite simplicial complex. We need this compactness condition, which is not available here. So this example is not applicable for our theorem. So now let us do an example which is applicable. So consider the real projective space of even dimension. So this is p to the 2n. So the torsion free homology is just the 0th homology. So as I said before, other homology groups are z modulo 2z, which we have to skip because we are only considering torsion free. So the lambda of f is this k greater or equal to 0 minus 1 to the k trace of phi k. Now we've already considered this 0th group. So minus 1 to the 0 time trace of phi 0, which is 1. So therefore this f has a fixed point. So you have a map f from p2n to p2n, it will have a fixed point. Now this same reasoning will apply to any space x. So obviously space x has to be compact if it has the same homology groups as the point modulo the torsion. So because if it is just like a point, then it will always be 1, and that will give you a fixed point. So now example 4. So say you have a map f from sphere to itself, and then we have the Lefschetz number. Again, you just copy this definition down right here. Now obviously the sphere has only two homology groups, h0, which is integers, and this is same in hn, and everywhere else it is 0. So hi is 0 otherwise. So again you will have minus 1 to the 0 times trace phi 0 plus minus 1 to the n trace of phi n. So notice that the map of the sphere from hn sn to hn sn, this map is just multiplication by an integer. So this is the definition of degree of the map f. So if you have a map f from sn to sn, this hn sn to hn sn is called the, so whatever you multiply here by some integer, say m, so this is called the degree of the map. So so the trace will just be, because it's just a single thing here, because it's just z here, z here, so multiplication by m. So this is the trace. So this is nothing but degree of f. So this is it. So if degree of f is not equal to minus 1 to the n plus 1, then f has a fixed point. So obviously if it is equal to this, then this thing will become minus 1 to the n times minus 1 to the n plus 1. So this is minus 1 to the 2n plus 1, which will give you minus 1. Minus 1 plus 1 will give you 0. Otherwise it is not 0. So it will have a fixed point if degree of f is not minus 1 to the n plus 1. Now finally a remark. So say you have a square matrix M, then trace of m raised to the power of p, you multiply m to itself p times, is equal to trace of m modulo p. So since this property is in the trace, this will carry over to our Lefschetz number also. So lambda fp is equal to lambda f modulo p. So this fp is nothing but you compose fp times f composed with fp times, and f is the map between finite simplicial complexes.